The topic of this screencast is vibrational normal modes. I'm going through the spectroscopy PowerPoint dated May 4, 2016. This screencast covers slides 15 through 26 in that PowerPoint. Okay, so why normal modes? A couple reasons. Fluorescence spectroscopy is influenced in a number of ways by the vibrational properties of molecules. Normal modes are a very elegant, relatively simple way to understand the vibrational properties of complex molecules. The vibrational properties of molecules are reflected in infrared spectra. Those are up here. I'll come back and say more about that in a moment. Another reason is that the math underlying normal mode analysis is really quite elegant. It's an example of how you can use a relatively simple physical model, a basically Newtonian physical model, combined with pretty simple matrix algebra to describe fairly accurately very complicated phenomenon. And so that's another reason to study this. It's a classic, really beautiful application, beautiful kind of physical theory because it's simple yet powerful. Okay, so what is a normal mode? A normal mode is a collective movement of a number of atoms in a molecule. And so what does that mean, collective? Well, that means that, for instance, this carbon-oxygen bond is going to be moving synchronously, let's say, with this carbon-carbon bond in that oxygen-hydrogen bond. And so what we will see is that there will be a collective oscillation, a simultaneous coordinated movement of all of these atoms together. The relative amplitude of their movements will be different. We'll be having a vector, the normal mode amplitude vector, that describes the relative magnitude of their movement. But they will be moving essentially that coordinated movement with set relative displacements of the atoms will behave like a simple harmonic oscillator. So you will have something like a simple harmonic oscillation of a set of atoms. We can observe that if the transition dipole moment changes, if the dipole moment of the molecule changes over the course of that oscillation, it is observable in an infrared spectrum. So that's another thing we're going to try to wrap our minds around and at least try to understand a little bit of the math behind that. Exactly why and how is that we need a change in the dipole moment of this molecule for us to observe it via absorption of light, light putting energy into that vibrational mode, as it's called. Okay, so the infrareds, if you take a molecule and you measure its ability to absorb light in the infrared region, you will get typically some kind of spectrum. And so what you'll see is absorbances at defined wavelengths. So when people started doing this, interestingly, they would see that molecules with given kinds of functional groups, so for instance, over here, we have a hydroxyl group. Over here, we have a six-membered ring. What people saw is that in different molecules that had similar functional groups, the absorption bands, as they're called in the infrared region of the electromagnetic spectrum, would correlate to an extent with what kind of functional groups they had. So things with hydroxyls would often have things with a hydroxyl bound to a carbon would often have a feature around this frequency in the infrared spectrum and another frequency around this feature around this frequency. Things with six-membered aromatic rings would often have features in this region. Now, in different molecules, these things would move around a little bit. And individual molecules would also have other features that were unique to them. But there was some sort of reflection of local chemical properties in the infrared spectrum. All right, so let's think about where in the electromagnetic spectrum infrared radiation is. And so this spectrum is calibrated according to wave number. Wave number, as discussed in the previous screencast, is inversely proportional to wavelength and directly proportional to frequency. So as you go up here, this is higher frequency, higher energy, lower frequency, lower energy. 1,000 means 1,000 waves, in this case per centimeter. And that means the wavelength is then 1/1000th of a centimeter, or 10 microns, 10,000 nanometers. 3,000 wave numbers would be a wavelength of about 3.333 microns, or 3,333 nanometers. So remember, visible light is, let's say, goes from roughly 350 to 800 and some nanometers. And so this is sort of the next step in wavelength above, and the next step in energy below the visible region of the spectrum. And so interestingly, so you can actually take photographs in the infrared region. You might have heard about night vision goggles. And what those are doing is they're looking at spontaneous emissions in the infrared region of the spectrum. So as we go forward now and understand normal modes, we will be getting insight, of course, into vibrational spectroscopy. We will understand something important to understand when we try to look at the properties of fluorescence. And we'll be understanding something about infrared spectroscopy or night vision. And what's going on there is that the vibrational normal modes, thermal energy, is actually exciting the vibrational normal modes. So basically every one of the normal modes will behave like a simple harmonic oscillator, as I said earlier. On the atomic size scale, everything is quantized, and so the oscillations are described by wave functions. We'll come back to this in a bit, but the bottom line is the wave functions are quantized, and so the energy that you can have in a normal mode is quantized. We'll talk about the details in a bit, but essentially there are discrete steps up in energy, and so what can happen effectively is that molecules in an environment, let's say at roughly room temperature, there's thermal energy around in there. As things bump around, they can actually excite the transition from a lower energy normal mode to a higher energy normal mode. And so the energy then, this normal mode will go into a higher energy state. It will oscillate more. That energy can be basically emitted, but a fluorescent emission of an infrared photon. So you can, in infrared spectroscopy, photons will be absorbed and drive transitions between one vibrational quantum state and the next. That process can be spontaneously reversed and will spontaneously reverse with some frequency. And so that infrared photon can be kicked off spontaneously. In night vision, with night vision goggles or infrared with infrared cameras, you're actually seeing the spontaneous emission of basically infrared fluorescence. Infrared photons are being ejected as normal modes go from higher vibrational states to lower vibrational states. And so you can see those vibrational photons being thrown off. Again, thermal energy will spontaneously lead to these things being bumped up to the proper quantized energy states, and then they can emit a photon and bump down. It's a kind of fluorescence process. Okay, and so that covers an overview of normal modes. Probably a lot of that is not so easy to understand at the moment, but by the time we've stepped through the details, hopefully it will be more understandable. So let's just look at one important mathematical detail. We'll see that the math underlying normal modes involves treating all of the atoms here as in the bonds, treating the bonded atoms as masses on a spring. So the research level, sophisticated treatment of this is essentially approximating this carbon atom as one mass, this oxygen atom is a separate mass, this hydrogen is yet another mass, and that each one of these bonds will be treated as a spring, or as we'll see, a set of springs. And so basically, vibrational normal mode analysis treats the molecule as a set of masses coupled by springs with specific force constants. And in the end, that gives a force constant coupling matrix between the different atoms. And we'll use a simple mathematical technique called, and then we'll just use Newton's laws. Newton's laws force in this case it'll be a vector because in this case we'll have a vector of atomic coordinates, and we'll have a matrix of force constants between those coordinates. The product of the positional vector times the force constant matrix will be the force on every individual atom. We'll go through this in more detail. And that will equal the mass of that atom times its acceleration. So this is just Newton's law extended to treat a system of coupled masses on springs. And we will see, using a technique called eigenvalue analysis, relatively simple matrix algebra technique, we'll see that the solutions to this Newtonian equation have the following form. It'll be a vector. This vector is describing each one of these atomic coordinates in Cartesian space. We will see that this vector has, as a specific amplitude, right? So this is a vector of coordinates. This is now a vector of amplitudes for each coordinate. In the normal mode, each of those amplitudes will oscillate with a particular frequency. So a given normal mode will have a given frequency, and will have a given set of amplitudes of oscillation for each one of the atoms in this molecule. And so this is simply an amplitude vector. And so the frequency, the time-dependent component, is entirely in this cosine function. So this vector will set the relative amplitudes of oscillation, but the oscillation will all be basically in phase, or as we'll see later, it can be actually in phase or 180 degrees out of phase, but it has to be one and the other. So you will see basically synchronous, either in phase or out of phase movements of all of the atoms, and they will all be oscillating in a given normal mode. You will have a given set of relative displacements of the atoms in a molecule, and all of those atoms will be oscillating with the frequency characteristic of the normal mode. So again, the normal mode is characterized by a frequency, and that frequency will describe the coordinated, either symmetric, in phase or out of phase movement of all of the atoms. The relative magnitude of displacement for every atom can be different, as set by this normal mode amplitude vector. So that's probably a lot to swallow. If you think about the sort of overall mathematics of this, you will see that if we have n atoms, we have 3n coordinates. But because the center of mass of this can move in 3 dimensions, and this thing can also rotate in 3 dimensions, there are 3 basically positional, center of mass position coordinates and 3 rotational coordinates. And so those 6 coordinates eventually sort of drop out of this. We won't go into that into detail, but hopefully you can see how qualitatively, if we have 6 coordinates that describe the position and rotation of this, we're left with 3n minus 6 coordinates describing the rest of it. Those coordinates describing the relative movements of the atoms. The normal modes are a representation of those 3n minus 6 degrees of freedom by which the atoms within the molecule can move relative to its center of mass and its orientation. So when you do this matrix math implementation, basically just of Newton's laws, this is a fancy version of the ball on the spring. We'll go through the details shortly. But you go through this fancy version of the ball on the spring, and you get solutions that represent synchronous oscillations of sets of atoms with a particular characteristic frequency, the normal mode frequency. And this math tells you that the molecule will have 3n minus 6 normal modes. So we can take something of this complexity and describe its normal modes. This molecule has 13 atoms. 13 times 3 is 39. So this has 33 normal modes. Those normal modes will basically be describing what we see in the infrared spectrum. They will not all absorb radiation, because to absorb infrared radiation there has to be a change in the dipole moment in the relative efficiency of absorption, which reflects the magnitude of the absorption, will reflect the relative change in the dipole moment along the normal mode coordinate. Right? So this is sort of a lot to wrap your minds around. But I wanted to get it out before we go through the details to give you guidance as to what this was all going to be about. Hopefully with this guidance now, as we step through the details, it will coalesce in your mind in a way so that it all makes sense. And then hopefully also you can, through this, master some of the mathematical details and minimally understand the elegance of this approach to describing a complicated and important physical phenomenon. All right, so with that, let's move on. So what underlies normal mode analysis is the model of the Hooke's law spring. In the molecule, in the normal mode treatment, we are treating each one of these bonds as a spring, and so really this is just a more systematic and elaborate treatment of a set of masses on springs. So we are going to treat this bond as a spring that produces a restoring force that wants to sort of hold the relative distance between these atoms constant, well, at some equilibrium position. And so it is in the same way that going back to the whole sort of fundamental concept of calculus, in a local region of a function, you can approximate it as a straight line. If there's a minimum in a function, right, and so this atom has a preferred distance relative to that. If there's a minimum in a function, you can approximate that in some local region as a parabola. If the minimum of that function is parabolic in terms of energy, right, so we can say that there is a parabolic dependence of the energy on the coordinate in some local region here. If in some local region that is parabolic, if the energy if the energy distance relationship is parabolic, that is roughly like a Hooke's law spring. So that's what we're talking about here. Now, I guess one thing I didn't mention earlier, but should have before we move on, is that the magnitudes of these displacements are very small. The length of a typical covalent bond will be on the order of 2 angstroms. In most cases, probably a little bit less, but let's say on the order of 2 angstroms. Sometimes a little bit more. It's going to be in the 2 angstrom range. The magnitude of an oscillation of a normal mode in the vibrational ground state is going to be something like 0.1 angstroms. Right, so this will be, I'm sorry, 0.01, sorry, order of magnitude off, 0.01 angstroms. So the normal mode oscillation, let's say, when this oxygen oscillates as part of a normal mode, and what we'll see is that there's a normal mode that involves mostly the stretching of this hydroxyl group. That's why this is called the OH stretch, the hydroxyl stretch. There is a normal mode that, although it does involve some displacements of other atoms, the energy of it is primarily localized actually in this OH stretch. The magnitude of the amplitude of the vibration in the vibrational ground state will be on the order of 0.01, a hundredth of an angstrom. This bond is a bit shorter. The oxygen-hydrogen bond is a bit shorter than the oxygen-carbon bond. But this is still on the order of 1/100th or less than 1/100th of the bond length. So these oscillations are very small, even on the atomic size scale, but they are energetically important and observable. And we'll see in the next section that you can't really understand fluorescence spectroscopy without understanding something about this stuff. All right, so on now. So again, we're going to approximate this bond as a Hooke's law spring. So let's review the properties of the Hooke's law spring. We treated this early on in the thermo segment and foreshadowed the fact that we would be using this Hooke's law spring treatment to model molecular vibrations. At that point, we just sort of kept to the very, very basic parts of it. The Hooke's law spring is one in which the force is proportional, the restoring force is proportional to displacement from some equilibrium position, right? So Hooke's law spring has an equilibrium position. That would be the equilibrium bond length in the case of a molecule. If you make the bond longer, it tends to get pulled back. In practice, that's because the quantum mechanical energy function for the molecule with the quantum mechanical wave functions, when the nuclei pull further apart, the energy of those quantum mechanical orbitals will increase a little bit. If the energy increases, that produces a restoring force back to the point of lower energy, which is the equilibrium position. Similarly, if the bond gets too short, the energy increases. Let's step through to that point quickly. So if you have a restoring force that's proportional to displacement from some equilibrium position, what you want to do to find the energy stored in that displacement is, of course, figure out how much work is needed to do to move the spring. So what we're going to do now is we're going to simulate moving the spring some distance by exerting a force on it. That will involve doing a certain amount of work on it. That will be the energy that is transferred into the mass. At that point, if, as it were, we let go of the mass, the energy that we stored in the spring will now continuously interconvert between kinetic energy and the movement stored in the movement of the mass and potential energy stored in the spring. But the energy will come from the initial extension, and the amount of energy involved in the simple harmonic motion will correspond to the energy that was stored in extending the spring to its maximum extent, extending the bond, as it were, to its maximum length in the course of the vibration. So what we need to do then is to figure out that amount of work. We need to apply the basic law in physics that work is force times distance over which it's applied. We did this before. When you basically, we're going to take force times distance, integrate force over applied distance. That's basically integral of x dx. Of course, we know that's 1/2 x squared times the force constant 1/2 kx squared. And so the potential energy of simple harmonic motion classically is 1/2 kx squared, and x max squared, where x max is the maximum distance of displacement during the oscillatory motion. And so now we're going to think about what this means quantum mechanically, right? In this classical model, this is the you could have any distance of displacement, and you could store any amount of energy in the spring. When we go to the quantum mechanical situation, we're going to approximate the bond by exactly this math. But in a molecule, the vibrations are going to have to be quantized. So we're going to talk about that in the next slide. And this is sort of carried over from the earlier use for this for the thermo presentation. And now we move on to the next slide. So I guess before we talk about the quantization of it, let's just talk about the frequency of the motion, because that will become important when we're talking about vibrational normal modes. Of course, this is the same force equation we had before. Earlier, we integrated the force over the distance over which it was applied to determine the work done in setting the thing in motion, and therefore the energy stored in the vibrational oscillation. We also want to know its frequency, and so we can once again use Newton's laws. In this case, we would have the force on the mass is equal to the mass times the acceleration, right? Force equals mass times acceleration, Newton's law. And so in this case, we get negative kx, the restoring force, times the coordinate of the displacement from the equilibrium position equals mass times the acceleration of that mass, right? D squared x dt squared. So the way that we solve this very simple differential equation is with a trial solution. We'll just assume that the position of the mass as a function of time is described by a cosine function, right? That's the simplest oscillatory one. It's very simple. It's sort of one of the simplest forms of an oscillatory function. So we are going to assume that the mass is moving in time by a function given by a, some amplitude. What is the amplitude? Well, the maximum value of a cosine function is 1. So the maximum value of this would be a. And so a describes the maximum amplitude of the maximum distance of displacement, which is the amplitude of the oscillation. Well, where do we get root k over m? Well, when we take the second derivative of this cosine function, we basically will end up with, when we take the first derivative, we'll get 1 factor of root k over m. And when we get the second derivative, we'll then multiply in a second factor of k over m. You might just do this quickly on a piece of paper to keep me honest. And so when we would do that, we will then the second derivative will basically give us a factor of k over m. And that k over m will end up basically canceling out, right? But it properly solves this equation. So if you put this trial solution into this equation, you will see that it fits the equation. And so another way to do it, you could say cosine omega t, and just say that we're going to assume there's some frequency, and then you could solve this different. You put the trial solution into the equation, solve for omega. That would show you that omega for this equation is given by root of k over m. Right. So what is omega? Omega is the radial frequency. The frequency of the oscillation will be 1 over 2 pi times the radial frequency, right? And so basically, this very simple trial solution pumped into Newton's equations tells us the frequency of the oscillation. The radial frequency of the oscillation will be the square root of the force constant over the mass. So now we've, in the earlier slide, we considered the amount of potential energy the amount of energy stored in the simple harmonic motion. That energy continuously interconverts between kinetic and potential energy, but of course it's conserved, and so at all times you have the same amount of energy summed between the kinetic and the potential energy in the simple harmonic motion. The simple harmonic motion will occur with a characteristic frequency. For one mass on a spring, that frequency would be the square root of k, the force constant on the spring, over m. So we're going to see when we go on to complicated vibrational normal modes of molecules, we get the same kind of math. We're going to get something that looks very similar to this, only with something called the reduced mass. We will do that very shortly. Now, in a quantum, so this would describe the, in classical mechanics, this would describe the continuous oscillation of some mass. In classical mechanics, we could pull the spring initially to any distance, and assuming it's frictionless, it would just then infinitely undergo simple harmonic motion to that maximum distance. So in classical mechanics, we could have any maximum distance, and therefore, because the maximum distance gives us the energy stored in the simple harmonic motion, we could have any amount of energy stored in simple harmonic motion. In quantum mechanics, that is not possible. These things behave like waves, and so what we do is we have actually a wave function. This is a probability function describing the probability of finding the particle at a given point in space. It's effectively a standard interpretation of quantum mechanical wave functions, and so the displacement, the trajectory, rather than being described deterministically as a fixed oscillation in time, what we will get instead is a wave function that describes the probability of finding the atom, the mass, the atom at a particular position. That probability density function will follow effectively the spatial distribution you would get from the simple harmonic motion. And then, of course, the energy is quantized. So let's think about what that means. You cannot have, if the energy is, right, the amplitude of the maximum amplitude of the displacement in the simple harmonic motion determines its energy. If the energy is quantized, that means there are only certain discrete values of total displacement that you can get to keep the energy quantized. Now, in quantum mechanics, there's a principle of continuity. Wave functions have to be continuous, so you can't actually have the wave function have a finite value at some point and then drop to zero. The wave function is continuous. So quantum mechanical wave functions actually go into what are called energetically forbidden territories. So there are some complexities in here, but the bottom line is that as you go to higher vibrational quantum states, the range of position of the atom spreads out, and that means the extent of the wave function spreads out. Quantum mechanics does describe matter as waves. Waves have null points, right? The cosine wave goes through something with a zero in it. If you're describing the position of matter as a wave, actually these wave functions, these are actually the square. These are probability functions. The wave function would be something like a sinusoid, be some, but the standard interpretation of quantum mechanics is that the positional probability is given by the square of the wave function. So what you're looking at here are wave functions squared. That's why they don't go below zero. But you do have nodes, right? This is the ground vibrational quantum state. And we'll come back to in a moment to the fact that one principle of quantum mechanics is that these things in the end will never be standing still. There will always be some, even at zero, absolute temperature of zero, you will have some degree of, you will have a baseline or so-called ground state vibration of an atom. And so this is that baseline or ground state wave function. When you put more energy into it, you go to the it's the baseline energy level of the vibrational wave function. When you put energy into it, you go to the next, when you pump energy in, you go to the next vibrational quantum state. This is the next higher energy step up. The next sort of allowed amount of energy that the next possible quantized amount of energy into this simple harmonic oscillator. Now you have a wave function that actually has a node at the zero position. So it says in this vibrational quantum state, the probability of finding the atom at the equilibrium position is actually near zero. So this is one of the remarkable properties of quantum mechanics that I will note in passing without a deeper treatment and more time to treat quantum mechanics, it would be very hard to understand that in depth. But at the moment, what we want to focus on is that as you go to higher vibrational quantum states, of course, the energy goes up. It goes up in discrete steps. Every time you do that, the wave function spreads out. The wave function spreading out is the equivalent of having a larger amplitude of oscillation. So to cut down to something rather simplistic, the energy of these quantized vibrational states, you can prove, is going to be 1/2 plus n, where n is any integer from 0 to whatever, h nu. And so nu now is the vibrational frequency of this quantized harmonic oscillator or normal mode, right? And so nu is the vibrational frequency. And so this is an interesting and important pattern about quantum mechanics. Planck's constant, which relates, of course, the energy in a light wave to its frequency, similarly relates the energy of a matter wave to its frequency. And so what we will see, what you can prove, is that the energy of a quantized harmonic oscillator goes up in steps of h nu. Of course, in a sense, that's convenient, and they need to go up in steps of h nu for if you we have spoken about, and we will see in more detail in a bit, that the frequency of the light wave needs to correspond to the frequency of the oscillation in order for energy to be efficiently transferred from the light wave, right? Because energy equals work equals force times the distance over which it's applied. For energy to be transferred to a molecule, it has to do work on it. In most cases in spectroscopy, like all the cases we're looking at, the electric field of the light is pushing the charges in the molecule around. The frequency, for that to happen efficiently, the frequency of the light wave has to match the frequency of the normal mode. And so the quantum mechanical principles show that Planck's constant applies to both the frequency of the light wave in terms of relating the permissible the quantized energy of the photons, and then in terms of the matter wave, Planck's constant produces the same relationship. So Planck's constant times the frequency of the oscillation will match it gives you the energy change going from one vibrational quantum state to another, and that will also match then the energy of a photon of light at the same frequency. And so the coincidence of these things, well, anyway, they are the same, and so you can get transfer of energy from a light wave to a quantized normal mode. And so then the energy will go up again in steps of h nu. That will match the energy of the photon that is being absorbed. We can see from this classical mechanical treatment that the frequency of the oscillator nu is given by 1/2 pi square root of k over m. So what does that mean when we put this all together? Well, what it means that for the quantized harmonic oscillator, as opposed to the classical harmonic oscillator, where we could displace at any distance and just put more or less energy into it, right? We could displace it here or here or here or here or wherever we want to and just put a different amount of energy in it. In the quantized harmonic oscillator, we're basically going in discrete steps of displacement and discrete steps of energy stored in the oscillator. And so when you do the math, you will see that crudely speaking, the equivalent of the classical limit of extension is going to scale as the square root of n, where n is the vibrational quantum state, right? So you have a 0 vibrational quantum state. That's the baseline. You can't get lower than that. There's still some vibration. In fact, there's 1/2 h nu of energy in that vibration in the 0 quantum state, and then you can go to, and then all the higher quantum states, the first, the second, the third, the fourth, etc., they will all be stepped up by exactly h nu. And what that will mean is that the maximum extent of the vibration sort of increases as the square root of, proportion to the square root of n, the quantum state. In a quantized wave function, that won't be an exact sort of hard limit, but the wave function will roughly spread out proportional to that, something roughly equivalent to that classical calculation. Okay, so that's sort of a lot in one slide on the quantized harmonic oscillator. Again, as I've told you many times, these notes are not intended to be a textbook. They're intended to be a study guide. So hopefully now, having heard all of that, you will be able to refer back to this and use it, as a concise summary of the important points. Okay, now, next we have to step back to thermodynamics for a moment. And why am I doing this? Well, there's something called, we don't have time to talk about statistical mechanics, but one of the fundamental principles in statistical mechanics is something called Boltzmann weighting. Boltzmann weighting comes from something called a thermodynamic partition function or a statistical mechanical partition function. We're going to totally skip over the theory here, but you're going to need to know the net result. The net result is shown here. The probability of being at thermal what Boltzmann weighting says, and again, this emerges from sort of fundamental statistical mechanical theory. This says that at thermal equilibrium, the probability of finding a molecule in a state M compared to a state N will be proportional to the exponent of the energy difference between those two states divided by kBt. And so this is sort of a fundamentally important thing. At thermal equilibrium, you will see a distribution of populations that is effectively, goes down as the energy goes up, right? And so what this is saying, if you think about it, if E is if the energy of state, so this is the energy difference between state M and state N. If state M is at a higher energy, right? If E is greater for M than N, negative E, of course, E to the negative E will have a value less than 1. And so these Boltzmann weighting factors are really quite fundamental in statistical mechanics. And so what it's going to say is the relative population at equilibrium of particles in state M compared to particles in state N is going to be E to the negative energy difference between those states divided by kBt. Kb is something called the Boltzmann constant. T is once again absolute temperature. I think the easiest way to explain this, and all that we have time for now, is to point out that this looks exactly mathematically like what we got earlier on for the concentration ratio at equilibrium, right? This was saying at equilibrium in a chemical reaction, in a binding reaction at equilibrium, the concentration ratios are given by e to the delta G, 0, the free energy difference over RT. When we propagate down to the molecular level in quantized energy states, you can see it's the same functional form. Of course, negative delta G is well, here we're actually looking at the reactant concentrations over the product concentrations. That's why we have a positive sign in front of the delta G here. The delta G is the free energy. We've seen that that's more complicated than enthalpy. It's effectively capturing entropy, but it's an enthalpic phrasing of it. So the reason this is one of the reasons it's useful, it gets a quantity that behaves like energy, right? Down here, when we get to the molecular level and we look at Boltzmann's Boltzmann weighting in the partition function, we see that the probability of the relative probability of occupancy of two states is scaled by this Boltzmann weighting factor, which is e to the negative energy difference divided by kT. Over here we had e to the free energy difference divided by RT, but R is just kb times Avogadro's number, right? So this is effectively reflecting the same physics at the level of individual molecules that this free energy relationship, that this fundamental equation of equilibrium binding reflected before. But the important point is that the sign here is the important thing, in the trend. As energy difference goes up, population ratio goes down. Now, why is that important? Well, that's important because in the normal mode situation, when you go to higher vibrational quantum states, right, when you go to higher energy states, the population at thermal equilibrium of those states will be lower. In the exact at thermal equilibrium, the ratio of the population in those. So now we're thinking about it as an ensemble of simple harmonic oscillators, so a large number of simple harmonic oscillators. We're saying the ensemble of the simple harmonic, in an ensemble of simple harmonic oscillators, the population in the different quantum states of thermal equilibrium will go down as the energy goes up. They will go down exactly in proportional. The relative population in each state will be equal to E, Euler's number, to the negative energy difference divided by kBt. If the energy difference is positive, E to the negative energy distance over kBt is a value less than 1. The relative population of higher energy states scales essentially inverse exponentially with the energy difference between those states. So bottom line, cut to the chase, higher energy, lower population at thermal equilibrium. This is going to be quite important because we're going to see in vibrational spectroscopy that when molecules initially undergo electronic excitation, they go into higher energy vibrational states. During the course of thermal equilibrium, those higher the thermal equilibrium involves the greatest amount of the population being in the lowest energy vibrational state. The energetic differences here are such, if you put in the numbers, the energy difference between even the ground vibrational state and the first vibrational state is large enough that there is a much, much smaller population in the ground vibrational state. So this is quite an important point. At thermal equilibrium, most of the population, the vast majority of the population, will be in the ground vibrational state. Absorption of light can promote things to a higher vibrational quantum state. Sometimes thermal collisions can promote things to a higher vibrational quantum state. When that happens, the vibrational energy can be removed either through additional collisions that transfer that energy to something else in a solution, or it can be removed by actually fluorescent injection of an infrared photon. But the bottom line is that for thermal equilibrium, you can put a photon in one of these you can put energy in one of these excited states, but at thermal equilibrium, they will tend to decay to the ground state, because at thermal equilibrium, the population ratio between the higher energy state and the lower energy state will be inverse exponentially related to the energy difference. The energy difference between vibrational normal modes is such that at thermal equilibrium, at roughly physiological temperature, the overwhelming majority of particles will be in the vibrational ground state. So this will become quite important as we move on. So this covered this is, I think, a reasonable introduction to simple harmonic motion as it relates to molecules, and an overview of normal modes and how we're going to get, how we're going to use now. What we're going to do next is we're going to use these different, sort of theories and facts that we've developed to treat the vibrational motions in the infrared spectra of real molecules. And that's when we go on to normal mode analysis. So again, the normal mode is a coupled bond or angle vibration that behaves like a simple quantized harmonic oscillator. So this goes back to a slide we used earlier. We're going to see what the normal mode will describe sort of coupled movements of different atoms in a molecule, but it will treat each one of those movements as an individual simple harmonic oscillator or an individual quantized normal mode. It will turn out that although some of those coupled molecular vibrations extend over the range of the whole molecule, in many of them the motion involves primarily displacements of two atoms. Now you will see you cannot really have this bond, well, you can't have this carbon atom move in this direction without also changing its distance compared to this nitrogen, its distance compared to that carbon. And so normal modes will generally involve some degree of displacement of all of the atoms. But that can range in a given molecule. In a given normal mode, there could be atoms that are moving barely at all and atoms that are moving a lot. The atoms that are moving a lot will be the ones where most of the, the energy of motion and the potential energy is stored. And so that localization of normal modes to the fact that most of the energy in some normal modes will be stored in vibrations of individual bonds or chemical groups is one of the useful things about vibrational spectroscopy. It turns out carbonyl groups in general have one normal mode that involves motion mostly of this CO along this CO bond axis called the CO stretch or a carbonyl stretch. And although the frequency of that will move around in atoms with different in different atoms with carbonyl groups, that will move around a little bit depending on what's attached to it. You will find that there's sort of a characteristic frequency range that this occurs in, because in most atoms with carbonyl groups, there will be one normal mode that involves mostly the carbonyl vibration. So with that, now we're going to dig in a protein, that carbonyl stretch is called the amide 1 bond stretch. In a protein, another important vibrational normal mode is actually the angular rocking of this NH group, which is called an amide 2 mode. Okay, so this should all set the stage for our analysis and understanding at a deeper mathematical level of normal modes. And we want to see now mathematically what it means to have a coupled vibration of multiple bonds and lengths. And we want to see how those coupled vibrations interact with light, how their interaction with light requires a change in the dipole moment in the course of the vibration, and then that will be, I hope, a satisfactory conceptual understanding of what is happening in infrared spectroscopy. We're going to use that as because it's the simple example of how and why light can transfer energy to molecules. And so we're going to go on with that next. Okay, we've covered a lot of interesting and useful territory, but the best is yet to come. What we want to do to finish this up is understand the qualitative properties of normal modes and how normal modes interact with light. So those are our two remaining objectives, how they interact with light so as energy can be transferred from light to the normal mode. So normal mode is a collective movement of atoms within a molecule that behaves like a simple harmonic oscillator. So as opposed to just one mass on a spring, this will be a number of masses, atoms, connected by springs, bonds, that then oscillate together. And what we want to do is we want to understand what that means, and we want to understand some of the basic physical properties. Now, I am not going to go over the detailed mathematical derivations in this presentation. Instead, we're going to focus on what the math means. So we'll look at some mathematical terms and functions and just think about what they mean, but we won't actually be deriving any of the mathematical equations. I'll do that in a separate presentation. So Wikipedia has an entry on normal modes that actually is quite informative. When I first looked at this, I thought, well, this is a little bit too simplistic, and then I realized after thinking about it further and trying to explain it to undergraduates or graduate students that, in fact, the simplification is good because it really lets you see the most important part of it. When you simplify it, the math is still there, but it no longer gets in the way to the same extent. So this is quite a nice model system. So what we're going to do is we're going to simulate, for the moment, we're going to look at a system consisting of two masses connected to each other by a spring, and then each connected to a flanking wall by a spring. So it's two masses, three springs connecting together, two masses, two flanking walls. And you could think of this as sort of a local chemical group in a larger molecule. So let's say, don't worry about now that there's sort of boundary issues here that are hard to reconcile for the moment. But just say for the moment you have some big, very rigid molecular structure, and then you have two atoms attached to that big. So we assume the rigid structure is somehow here beyond the walls. This is some, let's say, huge molecule, rigid molecular framework beyond this wall and that wall. And let's say we have just two atoms. Each connected to each other by a relatively flexible bond, and then each connected to the rest of the molecule by a bond. And we're going to say for the moment all of these bonds have the same stiffness or force constant associated with them. So what we'll do is, in a different presentation, I'll actually go through the solution of Newton's laws of motion for this system. But what we will get out is we will get out a vector describing a time-dependent vector describing the motion of this pair of masses in this mechanical system, which again is analogous, could be considered analogous to two atoms separated by relatively flexible bonds to a much more rigid molecular framework. And so this could be sort of a localized normal, considered a localized normal mode something like, so a localized normal mode within a much larger molecule. And so what we'll see is the normal mode will be described by a time-dependent vector, right? So this is x at t. In this case, the vector will have two coordinates. When we go to an actual molecule, there'll be many more, but for the moment, it's just two coordinates. One coordinate is this is sort of a one-dimensionally constrained configuration here. So one coordinate is the spatial coordinate, the x coordinate of that mass. The other coordinate is the x coordinate of that mass. They both have equilibrium positions. We're going to, actually in the math, we will just ultimately be looking at the difference in the current position compared to an equilibrium position. But we will be looking at actually how the x coordinate of the mass varies with time relative to its equilibrium position. And so we'll have two spatial coordinates. So those two spatial coordinates will go into a vector. And so we'll have a vector describing this time-dependent oscillation. And what we'll see, what we can see, what it is actually derived right down here below you, is that a vector that properly describes this system has the form of some constant, C1 eta. We're going to use eta as the index for normal modes. So this is a constant amplitude. It's a constant. It will describe the amplitude of that component of the vector. A constant times a cosine function, just simple cosine omega n t plus phi. So this is simply a sinusoidal oscillation with a radial frequency of omega. We're going to call it omega sub eta because, again, this is the index of the normal mode. So this is the frequency of this normal mode. These cosine terms also contain a phase. In a single normal mode, that phase term is the same. So what we'll see later is that when we have number of normal modes, the phases of the different normal modes can be different from one another. But in a single normal mode, those phases are the same and can really effectively be ignored as we try to look at the essential portions of the math. And so what this says, so C1 is the amplitude coefficient for mass 1. C2 is the amplitude coefficient for mass 2. And so what this says is that both mass 1 and mass 2 will oscillate with the same frequency. The amplitude of oscillation can be different. C1 might be larger than C2 or might be the same. C1 could be positive and C2 could be negative. Now, if C1 is positive and C2 is negative, if C1 and C2 both have the same sign, these things are sort of both, right? Think about what that means. If C1 is positive and C2 is positive, well, the cosine function here is the same for both of these components of the vector. If C1 and C2 are positive, they are both going to be moving in the same direction. Suppose C1 is positive and C2 is negative. Well, that means the one mass would be moving this way while the other mass is going to be moving that way. So if they're both of the same sign, you have a symmetrical motion. They're both in phase. If they're of opposite sign, you'll have an anti-symmetrical motion. They are basically 180 degrees out of phase. So basically, in the normal mode, the different atoms in the normal mode will all be oscillating with the same common frequency, and they will be oscillating with the same phase in a single normal mode. But the different atoms can have a different amplitude of oscillation. These constants can vary. And they can also be either in phase or 100% out of phase. So in terms of the spatial distance, right? So again, they could either be both moving in the same direction with certain frequency or moving in opposite directions and be spatially out of phase. But notice they will all be oscillating at the same frequency and with the same phase in this cosine function. Okay, so let's totally skip the math, but just say that this for the moment. But this is the full solution of the dynamical equations for this system. And what does that solution end up being? Right, the solution is of this type. The solution is going to be a vector, again with and so we can represent this time-dependent vector as a time-independent amplitude vector, right? So this C eta vector would have just C1 eta and C2 eta. C1 eta is the coordinate of eta the coordinate of mass 1 in normal mode eta. C2 is the coordinate of mass 2 in normal mode eta. And so this is now an amplitude vector. It describes the relative amplitude and then whether or not they're at 100 perfectly in phase or 180 degree out of phase. Right? The amplitude and the sign here will determine the relative amplitude of movement of the two masses and whether they're in phase or perfectly out of phase in their movement. Okay, and then they will oscillate at the same frequency. And so this is what a normal mode is. It's a synchronous movement of multiple masses, atoms, all with the same frequency with varying amplitudes through the course of that oscillatory motion. And so if we use this sort of as a trial solution and just plug it into the proper dynamical equations, we will find out that we get two solutions, right? We have two masses that will give us two sets of equations. It will give us two solutions, right? There are going to be two masses, 2 degrees of freedom. We're going to have two dynamical equations, one for each mass, two solutions. So each solution will end up being one normal mode. And so one solution has a frequency of root of k over m. Of course, this looks very similar to what we got for the simple one mass on a spring. It is the same frequency, actually. And so one normal mode has that frequency, same frequency as it turns out as you'd have for just the simple one mass on a spring system. And then this is the vector describing the normal mode amplitudes. It turns out that this math is called an eigenvector problem. And so the frequencies end up being eigenvalues. Don't worry about what that means for the moment. The math is all up here. We'll go through it later. It's not that complicated. The eigenvalue is then the frequency of the normal mode oscillation. The eigenvector is the relative amplitude. So now in the full solution for this system, what do we have? Well, we have one eigenvector has 1, 1. What does 1, 1 mean? Well, 1, 1 means that in the course of this, sinusoidal oscillation, this will have the same coefficient as that. So when 1 is moving forward, 2 is moving forward, and they will be moving forward exactly the same amount. So if one is moving if one is moving, let's say this distance in the course of the oscillation, 2 will move exactly the same distance. Furthermore, because the signs of these things are in phase, are the same, these things will be in phase. And so basically these two masses will be moving with no change in distance between them. They're both moving exactly the same amplitude, so the distance between them will stay the same, and so they will oscillate. And you can see how, right, with that kind of motion, actually this spring is not either compressed or extended, and so what you really have are the two masses moving with a restoring force coming from this spring and that spring, and so basically we have 2m and 2k, and so 2k over 2m gives you k over m, right? So that's why this ends up boiling down to looking just like one mass on a spring. So in one normal mode, these two things are moving synchronously, keeping exactly the same distance between them in phase, and they're oscillating back and forth. Let's look at the other normal mode. The other normal mode has a characteristic frequency, as it's called, of 3k over m. So this is root 3 faster frequency than that. So the second normal mode will be root 3 faster in terms of its oscillation frequency. Let's look at the eigenvector, or the normal mode amplitudes for that one. In this case, the eigenvector, or the normal mode frequency, the normal mode amplitude vector is 1 minus 1. So although this moves, it means that these two, what does this mean? These things will move the same spatial extent during the course of a given oscillation, but one of them will be moving forward and one of them will be moving back. So this is called an anti-symmetrical stretch. The one we looked at before, where they're both moving back and forth together, that's called a symmetrical stretch. The anti-symmetrical stretch, they're moving in opposite directions, right? The coefficient for mass 1 is 1. That means this one will move forward. But coefficient for mass 2 is -1. That means while this one is moving forward, this one is moving back. They're oscillating in and out. They're oscillating towards each other and away from each other. And so that simple harmonic motion is what we would call an anti-symmetrical stretch. It will have a frequency root 3 higher than the frequency of the symmetrical stretch. Now, the general solution, the most general sort of motion of this system will involve a superposition of the two normal modes. So mathematically, these physics are work out properly if you have both of these things going on simultaneously, and they can be going on to different extents. So basically, we can mix this solution. In the classical system, there's no quantization. Of course, in the molecule, there's going to be quantization. In the classical system, we could mix this normal mode in some amplitude with that normal mode. That's why we have these coefficients here, C1, C2. If we change C1, the relative motion of the two masses will not change. If we change C2 in that normal mode, If we change C1, the relative motion doesn't change. If we change C2, the relative motion doesn't change in this normal mode. But we can have different values of C1 versus C2, and so we can weigh in a different amount of sort of this normal mode in that normal mode. And it's the combination of those two normal modes that provides the general solution to this dynamical equation. But what you can but in the end, it's fine that they can mix together. All that means in the case, suppose this were a molecule and these were atoms. All that means is that we can have both normal modes going at the same time. We can put a different amount of excitation in each normal mode. Any of that is possible. So for the classical system, the general trajectory with time, depending on how much you kick these things at time 0, the general trajectory of time could be a mixture with any relative amount of energy in the two modes. Of course, in the quantum system, they can still both be occupied. They can both move simultaneously, but the amount in each of the modes has to be quantized, going back to what we talked about before about the quantized harmonic oscillator. So this is an illustrative system to describe. This is an illustrative normal mode problem. And again, we can think of this crudely as two atoms connected to each other into a rigid molecular framework by flexible strings with the same restoring constant, and we get two normal modes, a symmetrical motion and an anti-symmetrical motion. Okay, so that is representative of a normal mode. So now let's think about what will happen when we go to a real molecule. When we go to a real molecule, we're going to have the mathematical description of the normal mode is going to be the same. It's going to be a vector with a set of scalar coefficients. Remember, these coefficients are real numbers. That means they can have different magnitudes and they can even have different signs, but they're all real numbers. If the signs are different, things can be 100% out of phase, but they cannot have intermediate phase. And so each normal mode will have a coordinated, perfectly in phase or perfectly out of phase movement of each of the atomic coordinates. Yeah, and those movements will happen with a characteristic frequency. All right, so let's go ahead and look at that mathematical framework in more detail. And so now, I'm going to skip this in this presentation. This is explaining the math of the. You folks told me you didn't know what a determinant was. This just explains what a determinant was. This is how you solve an eigenvalue problem. We're not going to worry about that for now. Okay, so now let's go back. Let's go into a real molecule. Well, in our little simple system of masses on the springs, we had two coordinates. In this molecule, which is phenol, we have 13 molecular We have 13 atoms, and because this is in three-dimensional space, each atom can move in the x direction, or the y direction, or the z direction, which would be out of the plane of the board of the screen. And so we have three coordinates for each of the atoms, and three spatial coordinates. Now, because what we're going to be coming up with, effectively, this is a classical mechanical treatment of the dynamics of these coupled bonded atoms, or which we treat as coupled masses on springs. The full spatial description of that, the evolution of the positions of all these atoms in space and time, of course, could be broken down into the motion of the center of mass, the orientation of the molecule, and then the motions of the individual atoms relative to the center of mass. The normal modes cause describe those relative motions of the atoms compared to the center of mass. And so basically, although we need 3 times 13 or 39 coordinates to describe the positions of all these atoms, 3 of those coordinates are described by the position of the center of mass. Another 3 are described by the orientation of the molecule in space. So basically, there's 6 coordinates that give you the center of mass and the orientation of the molecule. So we basically subtract those 6 out of the 39 atomic coordinates to conclude that there are 33 spatial coordinates to describe the internal motions or the normal mode of this molecule. So in general, it's going to be 3n minus 6, internal coordinates describing the normal mode. So we now have to have a vector that represents those coordinates. And there are a number of ways we could do that. We could just describe a set of atomic coordinate vectors. So basically we have a set. So in this representation, each atom has a vector pointing to it. And then for every atom would have its own vector. So we have a set of 13 vectors. we instead could actually have a sort of a vector of vectors, and so we have 13 atomic position vectors. We could put those together into sort of a bigger vector, a vector of 13 vectors with 3 components each, or we could have a vector that just describes the Cartesian coordinates of every one of the atoms. This representation is best for the normal mode because they generally have different displacements around the 3 Cartesian axis. Like, it turns out that this H atom is mostly going to vibrate in this direction, so we'll vibrate in X and Y, but it doesn't really vibrate much in Z. So this notation here, where we would just break it down into the coordinates of each individual atom, x1, y1, z1, all the way through x13, y13, z13, we have a vector like this describing the individual Cartesian coordinates of the atom. And then what we're going to say is, with time, the positions of the Cartesian coordinates change. So they will all have some equilibrium position, which could be described as x1 or y1 or x13 or x13 or z13. And then so we're going to say that we're going to describe each of these as the equilibrium position vector plus the displacement vector, or the equilibrium position coordinate plus the displacement coordinate. That displacement coordinate will vary as a function of time. And guess what? It will vary sinusoidally, and it will give us a normal mode. All right. So what will happen is, now we had 2 spatial coordinates and 3 masses. When we go on to a more complicated molecule, we will have the number of spatial coordinates that will be 3 times the number of atoms. And then what are the springs? Well, the springs here come from 2 things. Again, you can approximate the energetic consequences of stretching a bond or rocking the angle of a bond. Although ultimately that depends in the change in the energy of the quantum mechanical wave functions as a function of the different nuclear coordinates. You can describe the change in their energy as a parabolic function. If you're describing the change in their energy as a parabolic function, the restoring force relative to that coordinate will be a linear restoring force. So basically, if the potential is parabolic, the spring behaves like a Hooke's law spring. It turns out when you get to advanced vibrational spectroscopy theory, these restoring forces are not exactly parabolic. They just deviate a little bit from parabolic shape. And so the math, that makes the math a little bit more complicated. So in more advanced treatments of normal modes, there'd be a slightly more complicated treatment of the math. But it would boil down to the same basic, sort of kind of physics in the end, where you get coupled motions between sets of atoms, coordinated, simultaneous, in-phase or out-of-phase motions of all the atoms, in some manner distributed over the molecule, determined by what these force constants are. And so in the same way as I said before, that you can approximate any function in a narrow enough range as a straight line, any function with a minimum point in a narrow enough range can be approximated as a parabola. If it is a parabola, you have a linear restoring force. This actually works pretty well, even though it's a slight it's slightly inaccurate. It's in the end a pretty good approximation of the vibrational behavior of atoms, even if you treat all these things just as simple Hooke's law springs. So one set of Hooke's law springs are just the bond lengths. As the bond is extended from its equilibrium position, its energy goes up roughly parabolically, so that behaves like a Hooke's law spring. As I said earlier, the scale of motion in these vibrations is very small, typically about 1/100th of an angstrom in the vibrational ground state. But then you also have another kind of sort of restoring force or spring-like force, and that comes from the bond angles. So just to sort of pick and highlight one example, if we look here, right, there's this angle between the O and the H, the OC bond and the OH bond, there's an angle between them. That angle has a preferred equilibrium value. As that angle changes, you more or less get a parabolic change in the quantum mechanical energy of the orbitals. And so that bond angle vibration also behaves more or less like it would on a Hooke's law spring. So in the end, what's happening is we have the bonds coupling together the different atoms. We only look at the nearest neighbors. So the restoring force on this oxygen will depend, of course, on the location of that carbon. And on that hydrogen, their locations will affect the bond lengths. If this carbon or that carbon move, that would also change the bond angle. In this case, Actually, that's why you get such a that's why you get a mostly localized normal mode here. There is not much of a coupling of the hydrogen position to any of the to these other atomic coordinates. On the other hand, if you were to well, if the oxygen were to move this way, sorry, I'm getting a bit obscure here. If the oxygen were to move along this coordinate, right, actually this bond angle would change, right? And so that means that the restoring force on this oxygen, and if this atomic position would change, right, let's say this atomic position changes a little. If this atomic position changes a little, that angle also changes. So the bond angle influencing the angular restoring force on the oxygen depends on its spatial coordinate, and the angular restoring force on the oxygen due to this bond angle depends on its position, obviously the position of the attached carbon. It also depends on the position of this carbon. So you do have some basically restoring force terms that couple these two coordinates together. But on the other hand, when this thing moves, it were to move independently of any of the other atoms, which is effectively, what's happening at the core of a normal mode. Some of these things are moving while others are not. So if this one moves, it does not affect the angle, this angle at all. Similarly, this one up here moving, it doesn't affect this angle, although it does affect that bond angle. But the bottom line is once you get over here or beyond, the motion of those atoms doesn't affect these angles. But what you get then is you get Cook's law restoring forces between covalently bonded atoms and atoms that are one step away, because those affect the angular restoring forces. So what we're going to do, in the same way that we had a matrix of force constants here that we used to solve a dynamical equation based on a vector describing the time-dependent coordinate of these two masses, over here we have, guess what, a vector describing the time-dependent coordinate of every atom in the molecule. And then we have restoring forces that take the form of a matrix. This is a relatively sparse matrix because the force constants, it has force constants between atoms separated by 1 to 2 covalent bonds, but it doesn't have force constants beyond that, so most of the off-diagonal terms are 0. But in the end, what we'll do, the normal mode, we will have a trial solution yet again, in the same way that we described the normal mode of the two, the same way that we described the normal mode of the two masses on a spring. We assumed it would have a form of some amplitude vector times cosine omega t plus theta. Same thing here. Some amplitude vector times cosine omega t plus theta. Once again, the normal mode has a single frequency. All of the atoms will be in any normal mode will be moving at the same frequency, and it has an amplitude vector. But the amplitude vector can have different magnitude for each of the atoms, and so and it could be have some amplitudes that are coefficients that are positive and some are negative. So depending on the amplitude, you will have a greater or lesser motion of each of the atoms. They will all be oscillating at the same frequency. They will all be oscillating entirely in phase or entirely out of phase, and so you will have a delocalized vibration involving multiple atoms in the molecule. Now, in every normal mode, if you went down to some incredibly high degree of precision, you would see some probably contribution. Every normal mode would probably involve some motion of every atom. But the motion in some atoms can be orders of magnitude lower than the motion in the other atom. And so, for instance, as I said before, there's one normal mode for this molecule that involves mostly the stretch of this bond. As that bond stretches, you'll also see, these atomic, especially the nearby atomic positions, will change a little. But the point is, most of the energy of one normal mode will be in this bond. There'll be another normal mode where most of its energy is in this bond. But every normal mode involves a delocalized oscillation of atoms throughout the molecule. The energy can be more in some atoms than in others, but all the molecules will be moving either perfectly in phase or perfectly out of phase with the same at the same frequency. And so, and then of course, if these were really balls on a spring, you could put any amount of energy into one of these normal modes. But this is a molecular system; it will obey the laws of quantum mechanics. But each of those normal modes will behave like a quantized harmonic oscillator. So that simple, mass on a spring quantized harmonic oscillator we described earlier, its basic properties in terms of energy and wave function distributions will match those of the normal mode. Now, when we do all the math here and we crank through and we solve for the normal modes, what will we get? Well, if we have 3n coordinate vectors, again, we have to sort of factor out the motion of the center of mass and factor out the rotational orientation. There are elegant mathematical ways to do this. I won't bother you with them. A bit too complex for this course. But we end up in the end with a set of 3n minus 6 normal modes. So when we solve this eigenvalue problem, again, we'll talk about the math a little bit more later. When we solve this eigenvalue problem, we will end up with 3n minus 6 normal modes. Each normal mode will have the same form it had when we came up with these solutions. Each normal mode will have a characteristic frequency, and it will have a characteristic amplitude vector. The amplitude vector will describe the relative magnitude, amplitude, and sign of motion of each of the atoms in the normal mode. So the atoms can move sort of 180 degrees out of phase, but they have to be either in phase or out of phase. These are all real numbers, and all of the atoms will move with the same frequency. Now, in the molecule, you can have all of these normal modes going at once. You can have different amounts of energy. At very high temperatures, you will have different amounts of energy in all sorts of different normal modes. But for a molecule with 3n atoms, we will end up with 3n minus 6 normal modes. Okay, so that's more or less the end of the story. And so what are those normal modes? So how do we see those normal modes? Well, we see those normal modes in the vibrational spectrum, in the infrared spectrum. I won't talk about this again because it was talked about earlier on at reasonable depth, but just reiterate that some normal modes involve primarily more localized motions. The other atoms in the molecule will probably be moving if you could get down to a finer enough spatial scale, but the energy will be localized mostly into subregions. And so again, for something like this, you'll have a normal mode that is mostly this carbon-oxygen bond stretch. You'll have another normal mode that is mostly this oxygen-hydrogen stretch. You'll also have a set of normal modes called ring modes that involve collective oscillations of the atoms around the ring. For these, they will not be dominated just by one or two atoms. For these, you will have motions that are coupling together all the atoms in the ring, well, because the ring is covalently closed. But still, you will have some normal modes that are mostly involving coupled vibrations of the atoms in the ring with relatively little participation from the atoms outside the ring. And so if you look at different things within aromatic six-membered ring, a six-carbon aromatic ring, you'll see normal modes that are relatively similar in their frequency characteristics. Now, of course, the frequency of the absorption, as we stated before, has to match the frequency of light absorbed by the normal mode has to match the frequency of the spatial movement during the normal mode. That's because fundamentally the way that nature is quantized, light is quantized in the same way that matter waves are. More or less. This is a bit simplified, but to a first approximation, the math we saw before, there's 1/2 h, there's 1/2 plus n times h nu energy stored in the normal modes, the quantized normal modes of the quantized states of a simple harmonic oscillator more or less goes up in steps of h nu. Right, where nu is the frequency of the harmonic oscillator. The quantized energy in the light wave goes up as h nu, where nu is now the frequency of the light wave. So basically, the frequency of the because of a common quantization of everything, the frequency of the light wave has to match the frequency of the vibration. There's actually that is related to something called a quantum mechanical selection rule. The selection rule sort of determines when and how strongly light can excite an atom. One way to think about it is that actually the frequency of the light wave has to match the frequency of the vibration. Otherwise, the electric field does not stay in phase with the motions in the atom. With the motions of the atom in the molecule. So that's also that's one of the ways in which sort of classical principles and quantum mechanics principles and wave physics and quantization, all in the end match up together properly. But the bottom line is the quantization of the simple harmonic oscillator goes in steps of h nu, where nu is oscillation frequency. The quantization of the light energy goes in steps of h nu, where nu is the light frequency. The light frequency that's pretty much has to match the spatial vibration frequency for the absorption to take place and for you to observe it in an infrared spectrum. So I think this covers pretty much most of what I hope you will understand about vibrational normal modes. There is one more thing now that we need to wrap our minds around, and that is basically how the normal modes interact with light. And, well, the necessary requirement for the electric field of light to transfer energy into the normal mode. So I don't want to go through this in detail now, not the math. I don't want to go through the math in detail, but I just want to, again, the whole purpose of this lecture is to get out the points. What is going on qualitatively, conceptually? What should you understand? Okay, well, earlier we described, of course, we said that we can use an oscillatory a vector with sinusoidally modulated components to describe the spatial oscillation of the atoms in the molecule. The normal mode involves simultaneous in phase or out of phase spatial displacement of all the molecules, of all the atoms in the molecule with a typical characteristic frequency. And so now, how does that normal mode interact with a light wave? So one of the things we're going to do is we're going to look at how the dipole moment changes as a function of the so-called normal coordinate. Well, what is the normal coordinate? The normal coordinate is basically this sinusoidal oscillation, right? In the normal mode, all of the atoms are moving with this frequency. So basically, this cosine term is describing the progression of the simultaneous in-phase or out-of-phase progression of all of the atoms along the trajectory of the normal mode. And so this cosine term is effectively a normal mode coordinate, and this coefficient is effectively the relative amplitude of the motion of a given atom along the normal coordinate. So one thing we can do is we can use this dynamical description of the atomic motion in the normal mode to actually calculate the dipole, the molecular dipole at a given time along the trajectory, right? If we know the atomic positions, we can figure out what the dipole moment is at a given point in time, right? Because the dipole moment is simply the sum. For the moment, we're going to assume that these are discrete point charges on the atoms. The model at the moment is that every atom has a certain net charge. And this model actually, it's not accurate at the atomic level exactly, but it's actually not a bad approximation to just assign different net charges to different atoms. Actually, very sophisticated molecular dynamics and mechanics programs more or less make that assumption. So for the moment, we're going to assume the charge resides on the atom. If the charge resides on the atom, it's very simple to calculate the dipole moment. We just sum the charge, we sum the product of the charge times the position of the atom over all the atoms, right? And so when we do that over the delocalized normal mode, we get one sum that just ends up going over all the equilibrium positions. And so that, of course, would then just reduce to the dipole moment at equilibrium. And then we get this oscillatory component that follows. We get a component of the dipole that now oscillates over the trajectory of the normal mode, right? And so this cosine omega t term is now modulating this summation. This is a summation of the individual charges over the amplitudes from the normal mode coordinate. Again, there's going to be another screencast where I step through this math a bit more carefully. But the big picture is that what happens to the molecular dipole in the course of the normal mode, of course, you will have some value of the dipole at equilibrium. For a nonpolar atom, a molecule, it could be even exactly 0. For a polar atom, it could be polar molecule. Sorry, it could be much larger. And so you have the dipole of the molecule when all of the atoms are at their equilibrium points of vibration, but over the trajectory of the normal mode, the atoms move around, and the dipole moment will change. The dipole moment will change with a sinusoidal variation in time, basically described by the cosine that's term that describes the fluctuation of the normal mode. And so what we will then see is that the dipole at a given time can be described as the equilibrium dipole, the dipole with the equilibrium position of all the atoms, and then a sinusoidally varying term that will scale according to what we call the transition dipole moment. The transition dipole moment is effectively the derivative of the dipole moment with respect to the normal mode coordinate. The normal mode coordinate is effectively this cosine term. So what does the math tell you that this is? Well, it tells you that the normal mode coordinate, it tells you that the time-dependent variation of the dipole is basically the sum of the charges of the individual atoms over the amplitudes in the normal mode vector describing, the magnitude of the amplitudes in the normal mode vector corresponding, the magnitude of the terms in the amplitude vector corresponding to that normal mode, right? And so, again, I think it's easy to see, in this atom, in this molecule, rather, the hydrogen will have a more positive charge, the oxygen will have a more negative charge. Those will, of course, have a dipole moment. As the bond stretches, the dipole moment changes. All this is saying is that we can quantify the change in dipole moment along the trajectory of the oscillation, right? The cosine term gives the trajectory of the oscillation. If we just plug in the math describing the dipole moment, if we plug in the math describing the spatial change in the atomic coordinates along the trajectory of the normal mode into the equation describing the dipole moment, what we see is that we have a time-dependent term now in the dipole moment that varies with the same frequency as the normal mode, and that is described by the sum of the charges on the individual atoms times their amplitude terms in whatever the given normal mode is. And so we're going to call this the transition dipole moment. The sum of the charges in the atoms weighted by their relative amplitude of motion and sign. The sum of the charges in the atoms weighted by their coefficients in the normal mode vector will describe what we call the transition dipole moment. This is the change in the transition dipole moment basically along the normal mode coordinate. Okay, so this has been going on for a while, but we're almost ready to warm up. The next thing we can look at is what is the force that an electrostatic field, what is the force that an electric field, for instance, the electric field of light, what is the force that the electric field can exert on the normal mode? And this is relatively simple math. Again, I don't want to get into the details of the math now, but the bottom line is if we just look at the work that the normal mode, the work that an electric field could, the work that could be done on a normal mode by an electric field, right? It would be the force times the distance over which it's applied. For an electric field, force is just, the force on a charge in an electric field is just Qi times the electric field vector. And then in the normal mode, the atoms all move along a particular coordinate. They move along a set of coordinates described by the normal mode vector and the normal mode amplitudes. When you put this all together, what you'll see is that the work that can be done by the electric field on the normal mode is going to be equal to the dot product of the electric field vector in the transition dipole moment. And then quantum mechanical calculations can show you that actually the probability of the transition is going to be proportional to the square of that dot product. But this simple calculation will show that no work can be done on the normal mode unless the transition dipole moment is non-zero. If the transition dipole moment were zero, there would be zero work done by the electric field, as even if the electric fields was like, the electric field can be oscillating there, over the light can be passing through the molecule, the electric field can be oscillating. But unless the transition dipole moment is non-zero, unless there's a change in the dipole moment of the molecule in the course of the normal mode, the electric field cannot do work on it, right? So what is this saying? Let's go back for a moment. This is saying that if you're looking at the normal mode, for instance, of this carbon to oxygen bond, you want an electric field to do work on that vibration. For the electric field to do work on that vibration, basically the dipole moment has to change. In order for the electric field to push something in order for the electric field to push electrostatic charge around in a way that contributes to that direction of motion, the dipole moment has to change. Otherwise, the electric field cannot do work. And so that's what the math in the next slide shows. The math in this slide shows sort of the quantitatively how we calculate a normal mode. In the end, it's it's quantitatively how we calculate something called the transition dipole moment vector. The transition dipole moment vector is the change in the molecular dipole moment along the normal mode coordinate. Let's say the normal mode is mostly this CO stretch. It would look at the change in the electric dipole moment as that bond lengthens. You can see that because the oxygen is charged, there probably will be a change in the dipole moment as that bond lengthens. And so then this transition dipole moment captures the change in the molecular dipole moment along the normal mode coordinate. It's calculated quite simply. We'll go through the math later, but it's a simple term in the end. It's the sum over the individual charges times their amplitude vectors in the normal mode. That's pretty easily calculated. And then we can see that, we can prove that that basically the electric field cannot do work on the normal mode unless that transition dipole moment is non-zero. So unless there's a change in the dipole moment, right? The transition dipole moment captures the change in the dipole moment as a function of the normal mode coordinate. If there's no change in the dipole moment as a function of the normal mode coordinate, basically zero work can be done. If the dipole moment changes in the course of the normal mode coordinate, right? If there is a, change in dipole moment magnitude is along the normal mode coordinate. What this shows that the electric field can then do some work on the normal mode. If normal work can be done on the normal mode, well, then there's at least a possibility of energy being transferred from the electric field to the normal mode. That is ultimately the physics underlying this relationship, which is that which again, to prove the exact form of this, you need quantum mechanics. But the probability of an light-induced transition is proportional. The probability of having the electric field component of light induce a quantum mechanical transition is proportional to the dot product of the electric field times the with the transition dipole moment vector squared. And the transition dipole moment vector simply captures the change in the dipole moment along the normal mode coordinate. So that's sort of a lot to absorb. And we should dig through the mathematical details, but I wanted to break this up so that the first presentation covered simply the concepts, a little bit of math thrown in just because some of the concepts are sort of quantitative and spatial, but without going through the derivations. And then there'll be a subsequent screencast where we go through these derivations in detail. Those, however, will be broken up derivation by derivation so that they're shorter and focused on just wrapping your mind around individual sort of slightly complex mathematical things.